We'll get started. Thank you everyone for joining our session. This session is called RAN in the Cloud. We are going to show how RAN and machine learning can be run on the same GPU cloud, why you might want to do it, what the benefits would be, and how we actually implemented it using a variety of Linux Foundation networking projects. I'm Amar Kapadia, co-founder at Aarna Networks. And
I'm Shuvo Chowdhury from NVIDIA.
So the agenda is we are going to cover the concept and the motivation for that concept. Then we are going to go through the implementation and then talk about next steps and how to get involved. So I'll hand it over to Shuvo, who will talk through the concept and the motivation.
Go to the next slide. So I think today we know in the mobile operator, you have difficulty in revenue generation, right? Your revenue is flat. You are looking for cutting cost, and ORAN solution was focusing on saving cost and power and CapEx and OpEx. So we come up with a new idea that if your TCO is going high and your revenue is flat, and then it's very hard for making new monetization in the platform. And that's one of the things we saw as NVIDIA that we can help improve operators, right? And you can see here, traditionally, when a RAN traffic is hosted in any server or any kind of cloud or any kind of platform, we see the utilization rate in the peak hour is around 80%, but if you average it out in the whole day, the utilization is less than 30%. And that's the data from a real operator in Japan, right? So at night, the utilization go down as low as 10%. So you invest in a hardware that utilization is so low, and then you are trying to save costs, shutting it down. So we thought how we can help the operators, right? And that's why the motivation ran in the cloud. So if you go to the next slide. So we know that RAN, there are CRANs, there are DRANs, and CRAN is getting popular for dense areas, right? Where you have a city like New York, you have 1,000 cell sites only for one city. And we think that CRAN will have a major play where you have a lot of fibers. And by 2028, the CRAN market will grow. And in this CRAN, we see that if you can have a platform that can do your AI inference, that can do your vRAN, that can do your small-scale AI training, right? That can do your private 5G, that can do your video analytics for factories. You don't need separate platform for all those. You can run everything in the same platform. And we call it unified GPU accelerated platform. And I'll explain why we think this is an approach that can help operators going forward, right? We took a use case in US. Overall, we have around 450K sites, right, in all operators. And for 50% of the sites, if we actually utilize a platform, which is GPU-based or accelerated platform, and with the same platform, if you can utilize and harness the capacity at the night time, we can generate new revenue, right? And new revenue will come how? It will come from the enterprises who want to do inferencing, who want to do other AI workload in the same platform, right? And even in USA, we found that it's a $50 million market in day one, right? And globally, it's $1 billion market. And that's a new revenue operators can tap into, right? So if we go to the next slide. So we came up with this idea. We call it AI and 5G data center. And you can think about it as an edge data center that can sit in central offices, that can sit in sites in a metro, right? Or even in a site like you have a lot of traffic going on in a stadium or something for private 5G use cases. So what we found out in a single server, with the GPU, you can have up to 20 peak cell sites, right? And 20 sites means there are a lot of servers now traditionally, right? With accelerator and other ways. But we found out GPU is very capable of doing parallel processing. And even with 20 sites, you will have a lot of capacity left for AI workload because GPU is multitasking and multi-threading, right? And what we are using this all open source, our CUDA software platform, to bring in our RAN workload from our partners DU, CU, and we can also accelerate our UPF, the platform we have called DPU, right? So we build this platform which will have ARM CPU, which will have a GPU from NVIDIA, and then it will have DPU and a switch also from NVIDIA called a Spectrum switch. So what will happen, that same platform, you can utilize any kind of workload that will be served by the operator or any other enterprise. So I'll show you a use case that how we can use computer vision or GenAI use cases, and it can be bring from global scale to that operator, right? Because we are saying that we'll bring you AI workload, but today operator don't know where the AI workload sits, right? But NVIDIA works with many thousands of companies who are looking for inference to be resolved as close to as possible, right? Places. So what we actually build a framework where we can bring in global scale AI traffic for the telcos. And if the telcos can do sharing of RAN and the AI hardware with proper isolation and security, their platform will be paid for within 2 years with the revenue they earn from AI workload. So what we are saying, virtually your RAN workload will be running free in the same platform because your revenue is not dependent on RAN only, right? So you now started have a new revenue model with this kind of platform, right? So let's go a little more deeper. So this is the average utilization, and this is taken from a real network in a time of the day. And you can see the green space is hardware is not used, right? Even in a dense area. And one of the use cases we can do, we can shut it down. We can shut it down the RUs, we can shut it down the server, but you already invested this hardware, it's sitting there. So what we think that the green thing now can generate revenue for you, right? So this is a very appealing use case for the operator. Then we heard the questions, yes, we understand we can generate new revenue, but where that traffic will come from? And who knows that I have a GPU sitting idle, right? So NVIDIA again came up with some new ideas. So the idea is we are building a multi-tenant infra, and this infra will have full 5G tenant as a first-class tenant, and it will also have a full AI tenant as a first-class tenant, right? And this platform is capable of running RAN, it's capable of running 5G core, it's capable of running any workload that NVIDIA today runs, right, for AI. So how it works, so you can think about, we have switches, we have our MGX server, which is our Grace Hopper-based new platform, and then we have Bluefield 3, which is our data plane accelerator, right? And then we can use any cloud OS. We are partnering with Red Hat and others. And you can see in the left side, in the right side, I think it's a very common stack. Who knows RAN, right? It's the full RAN stack. And we also build a SDK called Aerial. So Aerial can give you RAN layer 1 from any GPU, right, that NVIDIA has. Now in the left side, you can see that we have something called NVCF. And this is NVIDIA Cloud Function. So they build this Cloud Function. So in global scale, if you have some inference workload, it can be bring in as a traffic in this cluster, and your NVCF agent will discover if you have excess GPU capacity, right? So if somebody is playing game or somebody is looking for something, ChatGPT inference, it can look for it, it will be in the queue, and it will find available capacity, it will resolve here. And then in the nighttime, it's doing that. In the daytime, it will know that it needs traffic for RAN. It will release the server, and it will give back to 5G. So in that way, your platform is always utilized. So simple cloud concept we are bringing in the 5G space and 6G, right? And you can think about this is very simple, why it's not done before. So there are a lot of innovation happen in the background. So you can see that cell sites always connected with the server, and it was never dynamic because your RU is connected with MAC address. Now we actually did a lot of innovation in the switch. If you actually go server to server, consolidate the RAN, now you can move to any RAN to any server. Your MAC address will be mapped in the switch automatically, right? And that's where the orchestrator is very important, which understands the workload, not only 5G, but also for AI. So it can actually work like a broker and monitor the 5G workload and RAN workload and make a balance. And how this is done, Amar will share little more details, right? But we can have Q&A here, but one of the idea is this NVCF platform is serverless. That means the customer who is using AI inference, they don't need to know where it's getting resolved. They will just have a workload. I want to generate an image or generate a video, or I want to have a question to ChatGPT. And it will find a space, and it will actually resolve it. And today, stable diffusion and all those kind of workload, NVIDIA resolve the same way in a cloud network globally. So you don't know where it's coming from, but it's distributed, right? So we want to bring that technology to the RAN and the telcos, so telcos can become, we call AI factories. They can generate new revenue, right? Next slide. So this is the concept. It's a very simple. If you have a Kubernetes cluster, you can bring your own cluster, and NVIDIA will install something called NVCF agent, which will actually make it discoverable globally in this request queue. And then NVIDIA developed this NVCF API, which can bring in traffic to any cluster that exposed to this NVCF agent, right? So with this help of this, so if you have a extra capacity of GPU somewhere, we can always add it as a spot basis and then delete it when you need it back, right? And today, if you see Google or Amazon, they sell $3 per hour for GPU rent, right? So if you take that rate or even take $2 per hour, one rack of server we found can generate up to $4 million only in a single site or single central offices, right? So in that way, we feel that telcos have now found an opportunity to grow again with utilizing, become a broker for AI and become an AI factory, right? So we wanted to share this, and then Amar will share how we work together to make it happen in the real world, right? This is the last slide maybe I can share is, this is already done, and we are using it as a service. So NVIDIA will become a cloud service company. So you don't have to think about how I will build the model, how the inference will be done. It's an API. NVIDIA already make all those inferences as API. And you can bring your own inference model. We will make a pod. We'll install it. And then we optimize it. We'll run it in the platform. And when it's not needed, we'll delete it, right? So these all things are done as a serverless API through the cloud, right? And then 5G is just another workload, and end-to-end orchestrator is managing the whole platform, right? So this is our vision for next generation data center, especially in 6G, when you have millimeter wave and MIMO and all this complex activity. And we feel that your AI will not be only on the RAN, it will be in layer 1, it will be in layer 2, it will be in layer 3, it will be in the SMO, it will be in the RIC. And also, parallel, there will be AI not related to 5G at all, right? So you need a lot of processing power in the edge, and we think this is where we can actually build the next generation platform, especially looking forward to 6G, right? So Amar, maybe you can share details.
OK, so I'm going to go through the implementation. We used a variety of Linux Foundation networking projects to implement both the orchestrator and the SMO functionality. So in the first generation of the work, we are using an orchestration project called MCO from Linux LFN, Edge Multi-Cluster Orchestrator. We are using parts of the ONAP project, Open Network Automation Platform, specifically ANAI for inventory, active and available inventory, CDS for configuration, SDNC, SDNR for implementing the O1 interface of the SMO, and then Kafka for data collection and monitoring. Then we have Open Policy Agent, which is triggering the closed loop. So the closed loop to switch between RAN and machine learning workloads dynamically. And we have worked with commercial RAN vendors. We worked with Radisys for the first demo. We're starting work with Capgemini Engineering. But we have also worked with open source. So we have worked with Open Air Interfaces RAN for this as well. The future implementation, we are going to switch to Nefio. So MCO, CDS, SDNC, SDNR, we are going to deprecate all of that and switch over to Nefio. So it'll really be Nefio, OPA, Kafka, and Open Air Interface will be the next version of the demo. So this is what we showed at Mobile World Congress 2023, and then more recently this year at a variety of events. So what it's showing is on the left-hand side, you have 3 nodes. The first node is running the orchestration and the SMO software that I just outlined, along with the packet core. The second server is running the RAN software, CUDU. And then the third server is also running the CUDU. And this is the peak scenario. And when you go to off-peak, let's assume that one server frees up. So now what do we do? So we have to migrate the DU from server 3 to server 2. And now we have to make sure that the RU is now migrated over to that node, the connection, I should say, and talking to the existing CU. And then we have to orchestrate a machine learning workload on the empty node, the node that's now freed up. So we have to, the orchestration software has to do all of this and all the configurations involved, and then reverse the situation when there is peak traffic again. So go from left to right when the traffic drops, and then go back from right to left when the traffic picks back up. So there is monitoring, there's closed loop, there's reconfiguration, reorchestration. There's a lot of steps involved to make this happen. So what is the flow of the closed loop? So the flow is, first we have to create the Kubernetes clusters with all the day 0 configurations. We have to configure the front haul switch and the grandmaster with day 0 configurations. And that's all done via CDS and moving to Nefio. The admin user configures the threshold values on OPA, Open Policy Agent, so that the closed loop can be activated. And this could be something very simple, like look at the amount of traffic. Or it can be a lot more sophisticated. OPA is fairly versatile. Then MCO orchestrates the 5G core, the RAN functions, Prometheus on GNodeB servers 1 and 2. And this, again, will move to Nefio. Collectors monitor metrics from 5G core. We decided for this demo to use 5G core as a surrogate. But you could literally monitor anything. It's very flexible. And the metrics were used to trigger the closed loop. And once the closed loop triggered, then we had to migrate, reconfigure DU2 back to server 1, non-disruptively to the degree possible, reconfigure the front haul switch via CDS, and delete CU2. Now, the node is available. It's empty. It's available for machine learning. So now we orchestrate machine learning application on server 2. We started with computer vision. There's a framework that NVIDIA has called Metropolis. But more recently, we are doing inferencing with Triton and GenAI with NeMo. So these are all NVIDIA frameworks, Triton and NeMo, that are readily available. So we do that and demonstrate the machine learning application. And finally, we keep monitoring to reverse the situation. So that's how the closed loop worked. This shows a more visual way of what we just described, what we just went through. So we have MCO, CDS, OPA, and then workflow engine, which also I failed to mention. That's also from ONAP. It's called ESO. It's based on BPMN. And we have a distribution of all of that called Aarna Networks Multi-Cluster Orchestration Platform. That's the current one. And of course, like I've repeated myself many times, moving to Nefio. So we orchestrate. Step 1 is orchestrate core and RAN functions with Prometheus agents. Step 2 is start monitoring. Step 3 is we move the DU as per the policy, delete CU on server 2, configure the front haul switch, and then orchestrate the machine learning application. And then do everything in reverse when the traffic picks back up. So this is what we've done so far. There are a lot of deployment artifacts. In interest of time, maybe I won't go through each one by one. But to summarize, for orchestration, they are Helm charts. So we orchestrate the core, the RAN function, CUD using Helm charts. The configuration is done using CDS. So CDS has artifacts called CBAs, CDS Blueprint Archive. I think it's an unfortunate name. It doesn't really convey the meaning, but CBAs are for configuration artifacts. Then we have workflows using BPMN. So these are the 3 main artifacts. We also have some others like policies, et cetera, to trigger the closed loop. And so what the slide is showing is for each step of the closed loop, what were the artifacts used? So next step, I'll skip the first bullet. I've repeated it many times. We also want to add advanced functionality. So what we showed is already advanced. I mean, this is at the sort of the cutting edge of orchestration and SMO functionality. But we want to make it even richer. So things like failover. So if a particular node fails, then the RU can fail over to another DUCU. So we want to show that. We also want to show dynamic bandwidth adjustment. So when you're doing RAN, maybe the bandwidth you need to go to the core network or beyond is X. And when you switch to a machine learning application, you need maybe more bandwidth, less bandwidth. So that WAN bandwidth has to be dynamically adjusted. So those are the types of things we want to add to the demo. And in interest of time, we didn't show the demo, but these slides have been uploaded, so you can go see the demo. And if this is exciting and interesting, please join us. There are 2 ways to join. There is something called an AI RAN Alliance, which was launched at the Mobile World Congress by several companies, including NVIDIA, SoftBank, and many others, Microsoft, Amazon. So we have actually just applied. General membership just opened. So if this is interesting, please join. And the second is we are going to start bringing this use case to Nefio. So if you are active in Nefio and you would like to collaborate on this, again, please let me know, or Shuvo let Shuvo know. So with that, we will wrap up the presentation. Maybe we have just a few minutes for questions.
A couple of questions. One
Yes.
And if I may, just a second point, the whole idea of having a GPU at the edge and the green aspects.
Yes. So that's a very good question, actually. So I want to first share that every time.
Sometimes it happens.
Yes. Every time you think about GPU, you think it's energy hungry and it's very costly, right? But we did a lot of analysis with the operators. And what we see that today in the edge, everybody was waiting for a killer app, and it never happened, right? But today, the good thing is we don't have to find an app. If you have GPU, you can have GPU as a service, right? So what is happening that people are looking for GPU, especially startup all around the world, so that they can access and they can do their work, right? So that means you don't have to have an app, you just need to have how to monetize it. And then another thing, also thinking the forward-looking telcos, they're saying there will be 3 kinds of AI workload they have to handle. One is their own network AI workload, which is like optimizing RAN and other things. The next is their own HR and other, like their corporation workload, AI, which could or could not run in the same infra because of the security. But that's one of the things. And the third is if they go to the enterprises and they actually serve AI as a service, and that could depend on 5G or without 5G, because a lot of central offices have fiber connectivity, and it can come from any enterprise or hospital who need very quick inferencing, right? So what we see that telcos position in a very good way because they have a lot of fiber, they have a lot of proximity in the downtown area near a hospital. So if they can actually have a good platform, monetization is very, very easy compared to that. And regarding the green, we don't want to like make it like a very expensive and very, how I can say, it's not economical. What we found, if you have a dense RAN workload, the GPU stack we built can give you the best-in-class gigabit per watt. That means with the same gigabit, even with the ASIC, we can do better. But you have to bring in a lot of traffic, right? So more the traffic, more complex your workload, GPU shines better. And we think with MIMO and the way 6G is going, it will be happening, right? So it's just a matter of time. But all our calculation and our implementation shows that GPU is doing better and better because it's all software, right? So, yeah. Yes, so there are a few demos done. So the one we did with Radisys stack. Yeah, and then the other demo we did with Capgemini. We are working the same implementation with Fujitsu. And also Mavenir have an implementation. Those are public. There are non-public also work going on in the background.
I'm thinking because you mentioned of O1. So I think you're getting all those, the layer 2 PRB metrics and all through O1. Is that, how are you knowing the utilization of the radio there?
So this current demo monitors the core, but you could monitor the
PRB
RAN using O1.
Yeah, so PRB through O1, yeah, that's right. We are also trying to expose layer 1 because we are building layer 1, right? So we are exposing layer 1 also information, including DU, consolidate. So those is standard is not identified yet, but we are using like open source and REST API and FAPI and those kind of things to come up. But we think that that will be part of the work item in the ORAN and others, because that needs, we see that not only DU or upper layer RIC, you need information from layer 1 and layer 2 and a scheduler, right?
Yeah.
So just to add, NVIDIA also released something called 6G Developer Platform last week. So that has the full stack open sourced, so everybody can download and play with it. And it will also have a link level simulator, which has Siona, which is an end-to-end link level simulator. And third thing is, they also added something called digital twin. So we actually build a real-world RAN mapping in digital twin. So with EM solver and real-world propagation model, right? So whatever you're doing in the pipeline, you should be able to see those and play back. So we think that in future, you need that kind of platform to have a lot of processing and AI happening in the same location.
And next year, I think you're still going with that.
Yeah, I think initially he'll be on there. Yeah. All right, thank you.
Thank you.